Let's do one more. I think it's even one that you can pause and try right now and then restart the video and we'll go through the answer together. We have a fraction here, but let me have you just take a stab at it, okay? Do it. Stop the video and try this one, and then we'll look at the answer. I really hope you did try this one. What I would do with this problem, I see sets of parentheses with exponent outside. First, I'll take this exponent and work it in to every base in the parentheses. That will give me a 3 to the third, an x to the sixth. Those will both have to still be in the numerator of this fraction. Y to the third, and that has to be in the denominator of the fraction. So far, so good. This set of parentheses, we have an exponent of 2 that we are working in. That's giving us 2 to the power of 2 and x to the power of 6. Remember, when we're working these exponents outside of parentheses, that's the multiply. And then when we get to this step here, that's when we add. Now, what do you think about what we see here? I would like to tell you that when we have some expression that does not look like it is in a fraction, it basically works like it is in a numerator. So when I see this, I basically think that all this 2 to the second x to the sixth is just like the numerator of a fraction. And you want to know why that works? Because remember, any whole number, we can make it into a fraction by putting it over 1. So I can very clearly see that it really is like a numerator. And this denominator of 1 is not going to change anything because y to the third times 1, still y to the third. Anything times 1, it is what it is. Okay? So you can either, again, if it works, make this a fraction over 1. But you can always know that if it's not in a fraction, it works like it's in the numerator. So let's proceed and deal with these numbers. 3 to the third, that's 27. And here we have 2 to the second is 4, and we'll multiply those together, and I get 108. Next variables, I have x to the sixth, and then another x to the sixth, and I can put those together and get x to the 12th. In the denominator, I have y to the third, and that's it. You could say, well, is it y to the third times 1? I'd say, yeah, for sure. 1y to the third, but it's, again, when that coefficient is 1, we usually don't see it there. So y to the third is what I have in my denominator. And that's the answer I like for how we can simplify this expression, this multiplication up here. We've done a great deal of work so far studying exponents. There's still a lot more that we need to cover, however. Let's do a quick recap of some things that we know, the basics. This exponential expression, 2 to the third, we know that this means 2 times 2 times 2. We can even call that 8 when we do this multiplication. Let's look at 2 to the second power. That's 2 times 2 equals 4. 2 to the first power. I got a thing going here. I'm going to keep taking my exponent down by 1. 2 to the first power, we talked about how that is just a single 2. Well, I have to think now, what happens if I take my exponent down even further and call it 2 to the power of 0? Well, we like our rules to always work with each other perfectly. There has to be something that we can call this 2 to the power of 0. The reason I'm making a big deal right now is because so far this was very clear to us. 2 to the power of 3, that it told us it's 2 multiplied over and over again, and it's there 3 times. This is 2 multiplied over and over again. It's there just 2 times. Here it's there just 1 time. So what happens when it's not there at all? Do we call it 0? Well, we really don't call it 0. It doesn't equal 0. Let's try to find a pattern that we have here. When I look at 2 to the third and then I look at 2 to the second, what I've done is I've taken 1 2 away. And since it's all multiplication, the opposite, when I remove this times, it's the same as doing the opposite, which is dividing. So remove a 2 from this list is like dividing it out of the answer, because they are all multiplied together. If I remove it, it's because I did the opposite of multiply. I did divide by 2. And when I go from this 2 to the power of 2 down to 2 to the power of 1, I remove another 2, I divide another 2 out. So this pattern is telling me that each time I remove a 2 from this list, I'm taking my final answer and I'm dividing by 2. That's what's happening when I remove this 2 from a list of multiplying. It's because I did the opposite, divide by 2, divide by 2. The pattern would say, well, what happens when you divide by 2 again? 2 divided by 2 equals 1. This pattern is telling us that 2 to the power of 0 should equal 1. Well, one way that we could look at this is, well, does it mean that there was really a 1 there all along? That when I remove a 2, or remove a 2, and then remove another until there's nothing left, there's still a 1 behind? I think that's a decent way of looking at things, because what happens when we multiply by a 1? No change. 1 times 2, 2. Here's a 2 times 2 is 4, but times 1, still 4. So we can begin to think about 1 being a good building block for these exponential expressions and all these multiplications that we do. But not 0. What if we said that it should be a 0? Well, what would be here? 0 times 2, that would be 0. And 0 times 2 times 2, that would be 0. So 0 is really not what we would want to think about. The exponent of 0 tells us that we are down to our basic building block, which is a 1, because anything times 1 is still itself. And if we used 0, well, 0 just wipes everything out when you multiply by 0. So we don't use 0. Let's investigate a little bit more. We saw a pattern here with 2's. A quick recap of what we just looked at. Our lists, when we have it in exponential form, here we have expanded, and our final answer, we decided that this pattern we looked at told us that 2 to the power of 0 should equal 1. Let's look at when we use a base of 3. 3 to the third. 3 times 3 times 3 is 27. 3 to the second. So we are removing a 3. We're down to just a 3 times 3. 2 of them equals 9. We're maybe seeing this pattern that we're dividing by 3. When we remove another 3, now we're down to just 1 3. So 27 divided by 3, 9. 9 divided by 3, 3. We're dividing by 3's this time because that's the number that we're removing. We're doing the opposite of times 3. We're doing take it out of that list, divide by 3. Well, what would this pattern tell us about what 3 to the power of 0 should equal? 3 divided by 3 equals 1. We're seeing that so far numbers to the power of 0 should equal 1. Let's look at 5's just to look at one more example. Just the same patterns that we've been looking at so far, 5 to the third, 5 to the second, 5 to the first. We are seeing this pattern. We remove a 5 from the list and we divide by 5 in our answer. That last divide by 5 is again going to tell us that it should equal 1. How about we state this as a rule? A to the power of 0. Any number to the power of 0 equals 1. A quick note about this rule, that this rule doesn't happen to work when we have 0 to the power of 0. And that's actually an interesting mathematical question about what that does equal. But for now, we can say that it is undefined. And our rule is that anything to the power of 0 equals 1. Technically, it doesn't work when this number here equals 0, but to be honest with you, I don't think that we will really see something like that in the problems that we're working on right now. Let me talk to you a little bit more about this. It's now a rule that we have, that any number to the power of 0 equals 1, and we did look at a few examples where we could find a pattern that told us that something to the power of 0 should equal 1. But let's look at, does this really fit in with the rules that we've had so far, these situations that we've been establishing? Let's look at this. Here is an example where we have a multiplication. We do have the same base, 2 and 2. So our product rule told us that our answer also will have the base of 2, and that we just need to add up those exponents. So this would be 3 plus 0. Our answer would have to have an exponent of 3. Well, let's look at this statement. It's saying that some number to the third, and we know that's 8, but this number times something equals what we started with. 8 times something equals 8. Well, the only way that that could work is to do times 1. Anything times 1 equals itself. Our rule about exponents, that we add them together, it means that adding 0 should be the same as times 1. That we don't change the exponent, we don't change how many 2's are in this list, so we make no change to the exponent. We say, well, if you need to think of it as a multiplication, it would have to be times 1. That is the way that we do a multiply and we end up with what we started with. So another example just to support that a number to the power of 0, it really does equal 1. It's just to be thorough. X to the 4th times x to the power of 0. Same base, so again our answer will be x to some power. We add exponents in this case. 4 plus 0 is 4. So we're again seeing this multiplication where we start with x to the 4th, multiply by something, and it equals x to the 4th. We haven't changed the factor that we started with. And the only way that that happens is when we multiply by 1. So we're showing that numbers to the power of 0 equal 1, variables to the power of 0 equal 1. Really, anything to the power of 0 equals 1. I can't let you forget that there's this weird situation that 0 to the power of 0 is undefined, but we don't come across that very often. Let me have you try this example. It's dealing with exponents of 0, and it's also a good reminder about how do these exponents work when they're outside of parentheses or when they are not outside of parentheses. Let me talk you through this one. Here is x to the power of 0. The 5 is not a part of that. This exponent, it is only working on the x. Exponents work on as little as possible, only what they're touching. And in this case, just the x. So we have x to the power of 0 is 1, but it's still times 5. You could even think about order of operations. What would order of operations tell us if we know that between the 5 and this x is a multiply? And here we have exponent. Order of operations would say do the exponent first and then multiply. So this term right here, 5x to the power of 0, is really 5 times 1, 5. And it's a different situation over here where I look at that exponent and I say, what is this exponent working on? It's actually working on parentheses. It's working on everything here. Now I could say this is 2 to the 0 and x to the 0. Absolutely. We definitely could if you're thinking about what we were talking about earlier about exponent outside of parentheses has to work to every base inside parentheses. True, still true. But there's an even quicker way when our exponent is 0, and that is that it makes this entire expression equal 1. Okay? Different from what we had here. Here, this 0 exponent made just the x to the 0 equal 1. We had to still do times 5. But on this side, it's an entire quantity to the power of 0, so that entire thing equals 1. And the way we can finish this up is looking at 5 minus 1 equals 4. Interesting. Just different ways that we might see this exponent of 0 pop up. Let me give you 2 to try, so pause the video and work these 2, and then we'll look at the answer together. This first one, negative 3x to the power of 0. It's again a situation where it's an entire quantity to the power of 0, and that equals 1. The whole thing to the power of 0 makes it entirely equal to 1. And it's different down here because we don't have this 0 on a set of parentheses. Here it's just 0 on x. That makes it 10 times 1. And over here, this will be x to the 0. This is 8 times 1. What we're looking at, follow order of operations. This is 10 minus 8 equals 2. Interesting little expression that we have here, and it equals 2. All right, we're going to take it up one more notch, but